Alright, so I'm going to title this Magnetism. Okay. How many of you know what a magnet is? Everybody knows what a magnet is, right? You probably have a picture of like that horseshoe thing like this, right? Or you might have a picture of a bar magnet with a north and a south pole on it in your head. You might have a picture of your refrigerator in your head right now with all kinds of drawings from smaller siblings or from you on your refrigerator. Alright, so as you think about this magnet, you might also realize or remember that the opposite ends of the magnet would attract, right? What we want to get out of this unit is why. Why does that happen? Well, let's start with a review of the atom. You might be thinking, why on earth an atom? What does that have to do with magnetism? It has everything to do with magnetism, because inside the center of the atom is positive, and then outside the atom is this negative electron that is flying all around. Okay? Now, if this were the actual atom I was talking about, if, okay, this is an if scenario. If. Okay? If I have a negative electron over here, and there's only one electron, then there would be a negative charge on this side of the atom, right? What kind of charge would be on this side of the atom? Positive, right? Okay, so for this single teeny ridiculously small moment of time, we have a positive and a negative. Now, as soon as we unpause time and let it continue, this electron is going to be flying around so much that that charge equals out. Right? This is stuff you already knew. Excuse me, just a second. Alright. Now, what you might not also know is that these electrons have teeny little charges in them as well. Okay? We're going to get to that here in a second. But if the atom for a moment can have a negative side and a positive side, doesn't that kind of look like a magnet with a north and a south pole? Yeah. So let's put some words with this, okay? First word we're going to put with it is a dipole. Dipole means having opposite poles. Poles or charges on either end. Alright, the Earth has a dipole. We have a north pole and a south pole. Right? The Earth also has a magnetic field, which we're going to get into when we get into, I think it's lesson 3, it's Earth's magnetic field. Okay? So, if this atom were paused right here, we would have charges on either side. Okay? There are atoms that have something called a permanent dipole. And what does that mean? Well, that means we have a dipole, so we have opposite poles, but it's always charged on one side. I guess we could say always charged negatively on one side. But we'll just say charged on one side for right now. Okay, so if there's a permanent dipole, there's a temporary dipole. This atom is an instance of a temporary dipole. For just a millisecond, this electron is causing the atom to be negative on this side and positive on this side. For just a teeny little amount of time. That would be temporary dipole. This is permanent dipole. Permanent dipole is always charged on one side. Things that have a permanent dipole might be things like Fe, or that's also called iron. Okay. There's other ones, and we'll list those out here in a second. But iron, every iron atom has a permanent dipole. So let's kind of make a note of that. Every iron atom has a permanent dipole. Now you might be thinking, what do I care about that? You care about that because iron is what makes magnets. Okay, we'll also put that. A lot, we'll say a lot of magnets are iron. You guys probably have cast iron pans in your house that are not magnetic. You probably have paper clips, maybe some other things, I don't know, that iron things that are not magnetic. But every iron atom has a permanent dipole, and a lot of them make magnets. Now think for just a second. Iron is iron, that's what we call it. It starts with an I. Why is it Fe on the periodic table? Because its original name, its Latin name, is ferro. Okay? Right. Yes, sir? Sometimes it'll be the person that discovered it. Sometimes it'll be the place that it was discovered in. But yeah, so or sometimes it's a different language. So they start with a Latin or a Greek word. All right. Now you might say, well, why on earth do I care about that? And here's why you care about that. Because in science, in physics, ferromagnetism means that it's always a magnet. So we're kind of giving a bunch of words right now, but alright. That's like an iron atom is always a magnet. Okay? All iron isn't, but I'm gonna leave a couple of lines here so that I can draw something else here in a second that we're gonna talk about. But the next word that you need is anti-ferromagnetism. That means, what do you think? If ferromagnetism is always a magnet, what is anti-ferromagnetism? Not, right, never a magnet. Well, never is a strong word. But not always a magnet. Okay. So let's consider, we talked about this sort of imaginary atom that we could pause. Okay, let's think about this iron atom for just a second. If we think about one iron atom, okay, one iron atom, we'll draw its little periodic table box right here. We had a bell ringer question of this earlier. Okay, so if it has 26 protons, okay, and it has 26 positives in the center, how many electrons does it have? Well, it has 26 electrons. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a very bad drawing. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. If you look carefully, I put those 2 extra electrons on one side. Okay? The way that iron is laid out, it's kind of lopsided, just because of where it falls on the periodic table and its electron configuration. So sort of the houses that the electrons live in around this atom. So we think about our imaginary atom, it had a negative side and a positive side. Iron, because of these 2 extras, has a negative side and a positive side kind of all the time. Okay, so I'm going to draw my arrow to point to where that negative side is. These arrows show the negative side of the atom. So when we think about something that's always a magnet, the atoms in this kind of material line up all the same. Okay? Now, you might say, what do I care about that? Because if all of them are the same way, then we have a negative side and a positive side, and now we can have an attraction because there's a difference. This creates the dipole. So you might write that down. Or we'll put atoms lining up create the dipole. Now that word dipole, that means the positive and negative, the difference. Okay? So what do you think that the anti-ferromagnetism is going to look like? Anti-ferromagnetism is going to look like this. Notice how they're not going in the same direction. Right? So there is no lining up. Okay. Now, let's pause. If this is an atom, and these are electrons, and all of this has to do with where the electrons are, can electrons move around? Yeah, electrons can move around. So sometimes things that are not magnetic, okay, can be encouraged to have magnetism if an electric current is run over them. It can cause the electrons to start to go in the same direction. So we should write that down. If an electric current is sent over material, it can cause the electrons to line up. Oops, to line up. Okay? So that's a lot of writing for one day. We're gonna stop kind of right there. And let's look at what we're responsible for today.